All right. Is it April 4th or is it the 5th? It's the 5th. That's wrong. I don't want there to be mistakes this soon in the lecture. Well, I'm not going to. You know it's the 5th, right? This part, the presentation part, is so short I didn't bother printing any handouts today. Last week I printed them and didn't give them to you. This week I'm just not even going to print them. We're going to jump pretty quickly into the program, but I wanted to just put this up because your next homework assignment, which I'll give you at the end of class, that'll be due a week from today, and you'll submit it in the usual manner. The homework is going to be very closely mirroring the in-class activity that we do today. So I'm interested to hear how your experiences went with WMS. I know that you were having some trouble earlier with the outlet. Did you get it to work in the end?
Well, after I sent you the email, I went last year to get coffee, and back in the day I got back to the laptop and decided to update itself. Did not finish until the...
Oh, so it was doing Windows Update? Ah, okay. Well, better now than during the final exam. And I've had that happen before, students who had their Windows Update apply during the final exam.
I don't know why, I mean, it's usually asked for updating, but it's not.
Must have been an important fix. So the rest of you were able to successfully do the homework assignment?
I accidentally put an outlet somewhere random, and that just threw everything off
Yeah.
in 30 minutes. And I was like, well, that's wrong. And then just off my math, I was like, that's not working.
Yeah.
Delete it.
Yeah, and if you were successful in deleting that outlet, count yourself lucky, because sometimes when you drop one in the wrong place, it's hard to get rid of them. I mean, I usually just start over rather than trying to delete it and delete all the feature elements that it creates. You did that? Just start over. It's eventually faster. All right, well, listen guys, what we're going to do today is 3 different hydrologic models. Now these aren't the apex of where we're headed. Eventually we're going to do one called HEC1 and HEC-HMS. And those two are far more sophisticated than what we're going to do today. But the advantage of these models is that they're widely understood, they're quick to apply, and you kind of, you know, it would be silly to set up any one of these models outside of WMS if you already have it installed and all the data is available. So I want to show you how to do that. So let me give you the handout for today's 3 activities. There's a file on MU Online. It is an elevation model. Now it's not needed for this first activity. I think it's needed for activity number 2. The second demo we're going to work through today. But hopefully you have Wi-Fi on your computer so that you can get the data and also get the DEM that's there. So here's what we're going to do. We want to size a culvert for a rural watershed in Ona. And so hopefully after last week's demo and doing the homework, you're already well acquainted with how to be told where a project area is. And I'm telling you the location of the outlet here in terms of latitude and longitude. That way you can hover your cursor and see down here at the bottom of the screen, it shows the coordinate system. So the reason why in the handout I've given you the latitude and longitude is so that it can help you identify the project area. Now, we're going to start with the rational method for this, and the rational method is more commonly used for urban areas than for rural areas, and also it's better for small watersheds instead of big watersheds. And so this is a relatively big, and it's a rural area, but just as kind of a ballpark figure, we want to do the rational method on it. So I'm going to give you a few minutes to head down the road of identifying the project area, downloading the DEM, trying to locate the outlet, delineate the watershed, and then what we'll work through together is these bulleted points, because that's where that's the new material that I want us to all sort of be on the same page with. So I consider the review steps to be all the way through delineating the watershed, including running towpaths. So you can either do that through the tools, or you can use the wizard, whichever way is more comfortable for you. Should be about 0.4 square miles, I think, right? You can trim. All right, so here is the hydrologic modeling module, this button across the top. And it's meant to represent kind of like a diagram. And when we click on it, we have a new, let me switch off these display things here. Let me turn this off just so that it's easier to see. Oh, I still got the maximum flow distance on. All right. So see how it's called this Watershed 3B. It's just labeled that. The B means basin. And then here 5C is the outlet. And so it's a basin connected to an outlet. And that's kind of like the symbolic representation of our watershed. And remember that when you're in this hydrologic modeling module, it brings up a new tool here that identifies which model we're working in. So choose the drop-down box and switch it to rational method. And when you do that, and then switch, instead right now it's on select outlet, but change it to say select basin, and then double click on 3B. And it's going to bring up the input data that you have to give it for it to calculate the flow rate based on the rational method. So some of these things we have to either make assumptions on, or hopefully have some environmental data that will define, like the runoff coefficient. Other things we can compute based on the parameters of the watershed. You know, like time of concentration is going to depend on the slope of the watershed. And we don't have to estimate the slope of the watershed. It's going to know that just based on the DEM that we already downloaded. So first of all, let's set the runoff coefficient here to 0.6. And there's tables in your books that we've seen in previous lectures on, you know, what types of soil and what types of slopes and vegetation corresponds to different runoff coefficients. And so in the homework, I'm going to ask you to pick a watershed that interests you, or if you're completely uninterested, just pick one at random. But, you know, pick some watershed and do some models for it. And rather than just assuming 0.6 when you're doing the homework, what I'd like you to do is go into the textbook, and based on what you see in the aerial photo, like in your watershed, if you see a lot of grass, but then also some trees, try and come up with a weighted runoff coefficient that corresponds to real underlying data for the homework assignment. So for purposes of illustration, let's start with 0.6 as our runoff coefficient, and then calculate the time of concentration. You can enter it in manually, but let's not do that. We can do better than that. Let's have it compute it using the basin data. So if you click on that button, then it's going to bring up a series of different ways. There's so many different methods to calculate the time of concentration or the lag time. And what we actually want, we're going to calculate the lag time, and then it will convert from lag time to time of concentration. So in this drop-down box, choose the lag time, and then for the method, we're going to scroll down here and find the SCS method. And you'll notice here it has all of the variables that it knows, the watershed slope, the watershed length. But what it doesn't know is the curve number. And that's one of the input formula. Here's the formula. And so one of the input parameters for lag time is the curve number. So we can edit that. We can put in our own curve number for the value that it doesn't know yet, just by highlighting that. And so right now, let's say that we assume a curve number of 75 for purposes of calculating the lag time. Okay, so if you click OK, now here it's saying the result of the calculation is 0.26 hours. That's 0.26 hours for the lag time. When we click OK, then it converts it from lag time into time of concentration, and it puts it in terms of minutes. So it kind of does all of that in the background without us having to keep track of the units and the conversion factor, where time of concentration is 5/3 lag time and so on. So it knows the area, time of concentration. It still needs the rainfall intensity though. What's the formula for the rational method? CIA, Q equals CIA. You know, like if you walk out the door and you only know one thing for the whole semester, I hope it's that. It's just the easiest way to estimate the peak flow rate. And so here's the C, CIA. So the A it got based on the delineation we did. You know, the DEM combined with topaz combined with where we put the outlet. That's what defined the A. The C, we were guessing based on tables and aerial photos, maybe a site visit. So all that's left to define now is the rainfall intensity. And if you have a design storm in mind, you could type in, 3 inches per hour, and it would calculate the flow rate. But we can do something better than that. We can click here, compute, and then Hydro 35 data is, remember the precipitation frequency data server? It will go and get typical Hydro 35 data. So if you click Get Online Data, then it'll go and get some typical data for the eastern United States. Now, that's maybe something that we would want to, like, if we're being precise, we could get the exact IDF data for this project site. But remember that Q equals CIA is kind of a sloppy estimate anyway. So, you know, how the rainfall is different in Ona, West Virginia versus Canton, Ohio is probably the least of your worries when you're doing the rational method. You know, one is just that it's always conservative and overestimates the peak flow. The other being that the C value is hard to nail down. But this is a fair starting point for just some typical data. And the other thing is it knows the location, and so if you did compare the data here to what you find on the precipitation data frequency server, it may be exactly the same. But this is based on intensity rather than on the depth. Okay, so we've got the data, and this time of concentration here is what it's going to use to get the intensity. So if we click Done, now it's got the compute intensity. Right. Oh, okay. We have to tell it what year we want to do. And in the handout it says let's do the 10-year storm. So you highlight that row and compute intensity 3.2 inches per hour, and then that shows up here in the window. And so the peak flow rate is expected to be about 500 CFS for that watershed and a 25-year storm. Oh, wait, we did a 10-year storm, right? Yeah, 10-year storm. All right. So it'll calculate a hydrograph, and for the rational method, what does the hydrograph look like? Do you remember what's the implied hydrograph for the rational method? What will the shape of the rational method hydrograph look like? It's just a triangle. So if we do the traditional here, it will, in the background, create this hydrograph, and you can just double-click on it. It's not a lot to look at, but it shows here is the peak flow at slightly more than 500, the 514.8 CFS. The time to peak, it goes up and then it goes down. So that's the rational method. Now, one of the interesting things that we can do is we can break the watershed up into smaller pieces to get more accuracy. Because remember that once the water gets into the stream, it's moving a lot faster than when the water is just sort of flowing over the surface of the land. And so the more pieces we break this watershed up into, the more accurate the hydrographs are likely to be, because the area is actually referring to overland flow area rather than area that upstream of it is being served by channelized flow. So what we can do is we can put more hydrographs in. And by the way, the hydrograph that's there right now, we can delete that here in this menu that says hydrographs. We can do delete all, or delete previous would just remove the last one if you had multiple. So delete all, and then you can make changes. You know, if you wanted to adjust and see, well, what does the hydrograph look like if you've got 0.65? You change that, and it automatically adjusts the flow rate calculation down here. And then you have to click Compute again to get the new hydrograph. So here I just did one, a hydrograph at 0.65, and here's another one at 0.7. Compute hydrograph. And both of those hydrographs will be in the same view. So here is the 0.65 hydrograph. Here's the 0.7 hydrograph. But what we want to do is break it up into segments. So let's delete those hydrographs. I'm going to put it back to the standard runoff coefficient of 0.6 that it was at before. So I'm going to click OK on that. But I'm going to put in some additional outlets. And in the handout, it explains where to place those outlets. It shows that, here's the main branch. So switch back over to the drainage module, because right now we're in the hydrologic modeling module. If you switch to the drainage module, there's this left branch and the right branch of the stream. And we want to split this watershed up by putting one outlet here on the left branch and one outlet here on the right branch. So you can just click here on Create Outlet Point. And that's the same tool that you'd have access to through the wizard. You can drop one outlet on the left side, one on the right side, and then delineate the basin again. And you can get to the Delineate Basin button either through the wizard, or it's also here under the DEM menu, Delineate Basins wizard. So I'll do that just because we haven't done it that way before in class. Delineate basins. It's giving you the warning that when you delineate again, your existing watershed boundaries are going to be overwritten. So yes, that's fine, and just telling it to stay with the same units that I've done before. And so now I've got a watershed that's about 100 acres, another one that's close to 100, and then this one which is 66. So we've got it into pieces, and then the advantage of breaking it up into pieces, besides the fact that now each one of these hydrographs is going to be more accurate, is that then you could also apply different C values. So in the handout, I've given you some different C values and curve numbers to put in. So update your basins with that new data. I just want to show you one more tool. So you go back over here to the hydrologic modeling module, and if you double click on one of those basins to bring up the properties, you can see here are the properties for that basin. So you can go one by one and open each one of them individually, and that's fine. Or you can click one of them, and then instead of just show selected, you can change that drop-down box to show all. And then you can see all of the basins at the same time. So put in a different curve number and a different C value for each one of those basins, and then find out the flow rate for each one of the component watersheds. So you get the hydrograph for each one, and that's where we're going to leave it. If you have a hydrograph open like this, you can right-click and it brings up a series of options for exporting the data, and we are going to do that later tonight, but not for the rational method. So are there any questions related to just setting up the model and finding the peak runoff? The limitation with what we've done is that it won't automatically calculate the C value for you. And next week we're going to learn how to go online and get soil type and land use data so it'll automatically calculate the curve number. And that takes a lot of the uncertainty out of it. And of course the other factor that's kind of a weakness with the rational method is just the fact that the runoff hydrograph is triangular rather than being based on a unit hydrograph that has any sort of realistic distribution of like the rainfall over time.
Since this is a program not user-based and not hand calculations, why use models that are not accurate enough? Why use the rational method if you have something that can actually look at that?
Yeah. Well, sometimes there are like building codes and ordinances or just standards that are set that tell you you have to use a certain method. So, you know, there may be a requirement from the Division of Environmental Protection that when you're sizing the pond for a shopping center, you should use the rational method. And, you know, in an urban area, the rational method would work fine. And you can do WMS for an urban area. You know, when you have more pavement, then the C values are more accurate. But even when, you know, you'd be better off doing a sophisticated model, sometimes just the rules say to use something that's less sophisticated because it's been done that way for a long time and the people who are reviewing it understand the older methods. But, you know, I'm not saying just because I showed you this doesn't mean that this is the method you should do. I just wanted to show you so that you'd know that it's there and be acquainted with how to use it. And that's true, yeah. Like, if you do your design based on these peak flow rates, chances are it's not going to fail. So you could nail things down more closely with a more sophisticated model, but they probably, the flow rates won't be larger than what you get with the rational method. All right, so if you'd like to save that as an example, be sure to click the Save button because we're going to start with something new here. Now, the next method that we're going to learn about is called the National Streamflow Statistics Program. And this National Streamflow Statistics is the result of a really lengthy statistical study of what stream gauges there are in each state. And they periodically update these reports and give you a new equation based on all of the data that they have observed. And here are the stream gauging sites in West Virginia. You know, there are approximately 100 or so that go into developing the formulas that are behind the National Streamflow Statistics. And they divide the state up into 3 regions: Eastern Panhandle, the Central Mountains, and then the Western Plateau. And here in Cabell County, we're in the Western Plateau region. And for each of these 3 regions, they have a formula that's based only on the area of a watershed. And so if you know that one parameter, then you can estimate the flow rate out of that watershed for a 2-year storm, a 5-year storm, a 100-year storm, whatever. And it doesn't, now these, by the way, I should say that the name of this is for rural unregulated streams. And so if you use that formula for a watershed that has a lot of urban development in it, then the formula is inaccurate. Or if you use it for a regulated stream, meaning some sort of a water body that has a dam upstream of it, you know, the dam is going to throw off the flow rate when there's a storm. It's going to slow down what you'd otherwise see. So, you know, if you use this in the context that it's intended, the accuracy is about plus or minus 30%. And we'll see the standard error reported when we work through it tonight. So here's this, the three equations that you get. They're like exponential equations with area as the only input variable. So it doesn't take into account the curve number. It doesn't take into account the slope, not directly. You know, all of those factors are kind of built into the empirical equation. So in the handout, I tell you that there is a data file online. Let's see, yeah, a provided DEM. So you need to go into MU Online to get that DEM file. It's already trimmed for the area that I wanted you to look at. So it saves the trouble to identify exactly the watershed area. And it's a pretty large watershed. So go to, okay, so does everybody have that DM file downloaded? What you can do is just click on the open dialog box and browse to that location, hurricane DEM file.gdm. Okay, so if you open that, then you'll just see the standard elevation contour lines that we're used to seeing, where the high elevations are in the cooler colors and the low elevations are in the warmer colors. So at this point, you can immediately have it calculate topaz. And so if you want to work through the wizard, then you can go to the modeling wizard and save a new file. I'm going to call this one Hurricane. Save it. You need to skip over some of these things, like we don't necessarily need it to define the project bounds or get the watershed data. We've already got that. So don't do those, but we do want it to calculate topaz. And once it does, you'll notice that we've got our blue lines. If it's challenging to see them, then you can, of course, always turn off your DEM. Oh, it's not showing the flow accumulation cells yet. So zoom in. The spot where we want to drop our watershed outlet is this stem. You know, there's a couple of flow accumulation cells above it and below it, but it's, as it says on the handout there, we want to actually put it at the far western edge of this area. So you can create an outlet point and drop it anywhere in this zone here. I mean, if you're a little to the left or a little to the right, it's going to change the watershed area by a few acres is all. So pick this spot and then you can delineate. You'll notice down here it's giving you a status update on all of the calculations it's doing to delineate the watershed, and it's a lot slower than it was before because this is a pretty big watershed, and so it's chewing through a lot of data to find the max flow distance. It's calculating lots of different flow paths to find out which one is the longest from the watershed boundary back to the outlet. It'll take a few minutes for it to finish. Not minutes, probably be done in 10 seconds. You should just open it. So I don't cancel that. If you just open. Yeah. 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 You don't have to import it. You can just open it, and then it knows right where it should be. Yours delineated. Good. Uh-huh. That's because the right here, that's low. So if you change that to maybe 30 or 50 acres, then that'll solve it. So click up. Oh, you don't need to compute topaz again. You just apply to display after you change that. Yours is still calculating. All right. So this one's more than 50,000 acres. It's a big watershed. Oh, I accidentally dropped another outlet somewhere. The national stream flow statistics is, you can think of it as just a really broad regression that is going to be better than the rational method because at least it's based on physical observations. The rational method is that the limiting factor there is what C value you pick. But these are based on the real rain that was in the area and the real land use and soil type characteristics. And so it's based on good data. It's not based on assumptions, but there's a lot of variability. And so that when we look at the results, it'll be reporting this 30% error, which means that what you'd actually observe for a 10-year storm may be 30% higher or 30% less. The other thing that it'll calculate is something that's often referred to as probable maximum precipitation. And it's like the largest storm you could have ever expect to see in an area. And that's based on physically how much moisture could there be in the air, the size of the watershed. And that's when we're calculating this national stream flow statistics, it'll also calculate the maximum probable precipitation. It calls it something else. It calls it the max flood envelope, is what we'll see on the screen when we do it. But that max flood envelope is way far beyond what the national stream flow statistics is calculating. I think the NSS is only going up to the 500-year storm, but the max flood envelope is thinking like in terms of the geological age of the Earth. What's the largest storm you'd expect to see over the next 20, 50,000 years? How are we doing? That's all the stalling I've got in me. Okay, you're finished? Yours is still going? What percent are we at? 64%? All right. We're going to press ahead, and when it gets there, then you can catch up, because this is, I think, the only step that'll take a while. All right, so go to the hydrologic modeling module, and last time we were doing rational method. This time we're going to do NSS. And so you can do that same thing of double-clicking on the watershed, and then it will bring up some dialog. This time, though, it's going to look different than the rational method dialog did. So you see here it says National Stream Flow Statistics Method. So it's already copied over our basin area into what it needs to know, because all of the formulas are based on area. But we have to identify our state. So by default it says Alabama, but we will switch that to West Virginia. And then from the map, remember which zone we were in. In our case, we are in here the Western Plateau region. So we need to change the formula, the available equations. It's got some of the old formulas where they defined the boundaries differently. It used to be a north, south, and east zone. What we're looking for here is the peak flow Western Plateau region. And so click select and bring that over. Now we also need to identify the max flood region. So the max flood region is based on a slightly different map. I have that on the handout, actually. See this diagram here where it says maximum flood regions. So you can look at that and see that West Virginia is in region 4. At least the entirety of West Virginia is in region 4. So change that to say region 4. By the way, if you weren't sure, there's always this help button down here. And WMS has fairly good website help information. That map that we need to know which region we're in, once you click on the help button, eventually, okay, here it is. It should bring up a page that has that same map on it. So if we scroll down, here you can see there's that same map. Apparently it doesn't zoom in now. Okay, it does zoom in. All right, so region 4 for us. Okay, so we've got peak flow, Western Plateau, region 4. Compute results. That's the last step. It was right there in front of me the whole time. All right, so now what it's got is it's got the return period and the peak flow. So we can find out all of the return period versus peak flow. So if you wanted to know the 100-year storm, it's going to be 10,700 CFS. The 500-year storm, 14,000 CFS. All right. Now, on the handout, I asked you to do a couple of things. And so you can export this data by clicking the export button and save it so that you can open it up in Excel. And I give you instructions to create a scatter plot, change the x-axis to logarithmic, and then sort of a thought question as the last bullet point. So it's 5 o'clock, let's do this. We've been at it for an hour. Let's take our traditional 5-minute break, and then when you come back from that, start on exporting the data, opening in Excel, and then creating the graph of recurrence, which will be on the horizontal axis, and peak flow, which will be on the vertical axis. All right. So once you export that CSV file, then open it up with Excel. You should notice an interesting trend when you move the horizontal axis to logarithmic scale. There it goes. So I ask you a thought-provoking question, what I intended to be a thought-provoking question anyway. What does that mean about the max flood envelope? You know, we calculated some value back in the program for the max flood envelope. So it was max flood envelope 78,000 CFS. So how does that compare to what you've learned with this? Seems unlikely to me. Is your area the same? Do you have 80 square mile drainage area? 7 square miles? Okay, try this. Go back into the drainage module and DEM menu and do delineate basins wizard and click OK. Do it over again. Just click OK. Oh, yeah. I don't remember if your computer was fast or slow. It seems to be doing pretty well. Had you changed that to say feet? Okay, because this DEM file has units of meters. Let's see. And it might have remembered what you'd done on the homework. If I go into here, yeah, the XY unit should be set to meters. So yeah, go to where it's asking you. Okay, oh, you'll need to delineate again, I think. Mm-hmm. All right, so like you could do a trend line here and it'll have a pretty good R squared value, but what you'd need to do is a logarithmic trend line to get it to match the trend that we actually see. So if you display the equation in the R squared, a logarithmic trend line appears as a straight line when you have a logarithmic scale like we do. But you could use this to find out what's the relationship between recurrence interval and flow rate. But if you wanted to have, you know, like that maximum flow envelope that it's assuming, what was it again? It was, I think, 78,000, right? So if we go over here and say that we want to scale it to in the range of 70,000, and you were going to extend that trend line the entire way, then you're going to have to go, you know, like for this to continue all the way until it gets to 70,000, you're talking millions and millions of years. And so my impression is that probably that flood envelope, that maximum flood envelope, is exaggerated. It's on the high side. All right. So any questions about NSS? The last one we're going to do is TR55. All right, I'm going to let you work this one independently. I've given you the location, a description of the fact that it's in Charleston. And if you look on the map here, hopefully the interstate will seem familiar to you. It's north of Interstate 77. You can see the airport on the picture there. So it's immediately west of the airport. And the outlet that we're interested in is very near the intersection of Garrison and Crescent. So delineate the watershed, and then instead of NSS, open up the TR55 window and go through the process of estimating the time of concentration, putting in the curve number that's mentioned on the page there, and see if you can get a hydrograph based on TR55, and then we'll talk about how to export the data and play around with that.
These maps and some of these data serves that extend past the boundary of the United States.
Yeah, there are some world data sets for elevation. If you go to download data from web services, where is it? This worldwide elevation data, I've used this in the Middle East. The coverage extends there, so you can pick watersheds all over the world. Now, it's not always to the same resolution as we've got in the U.S. You know, this 10-meter resolution is pretty good. In West Virginia, we have an even higher resolution data set. It's called LIDAR, and it has a resolution of about 3-meter spacing. And so it's highly accurate, but this one's good enough if you've got a relatively large watershed and lots of relief, for mountainous areas. See this Bigley Avenue? When I saw Bigley, I thought it made me think of Donald Trump. You know how he says big league, Bigley. There was that whole thing during the election. Nobody knew what he was saying. Yeah. Did you have a question? Delete what? Oh, this is one of those cases where I think it's just easier to start from scratch, and it's not so bad because it will remember your area. Why do you want to delete it?
Because if I want to change the outlet.
The outlet location?
This is one of the lines.
Yeah, I think it's easier to start over. That's my suggestion. No, weird, right? It'd be nice if it did, but it doesn't. So you can go get it from the data server yourself. I would imagine they have a feature request list if you want to put it on there. Tell them your company demands such a feature as paid licensors. You're saying the precipitation data? I don't know. That's a good question. Yeah. So when everybody gets to this point, we'll go through the export process together, because, I mean, I've put the instructions there where you should change it to a text file on row versus column and so on, but if you get it switched, then the data gets a little bit screwed up, so it's important to be exactly right. Which one? Oh, to get to the TR55 thing? Yeah, it's select basin and then double click. You can also get to it through this menu, TR55 Run Simulation. The menu's changed a little bit differently across the top here depending on which model you use. And I say here, we did one at 68 and we also want to do one at 72 curve number. So I'm going to change the curve number here to 72. And of course that's also going to change the time of concentration. So, oh, it already updated that, 72. Anybody remember what the significance of this type 2 is? It's when you actually see the rainfall over time. Yeah, it's a regional variation. Yeah, let me see if I can find the slides where we had it before. Here it is. So it's referring to this graph where here is the rainfall intensity. Well, this is the cumulative distribution over time. And so, you know, here in the Midwest, we have these periods where suddenly the rainfall is very intense, in contrast to areas that are coastal, where they're less likely to have periods of really intense rainfall and more likely to have a pretty constant rainfall intensity through a 24-hour period. And so if we had changed it to type 1 or type 1A, then the peak flow rate wouldn't be as high, because what this is doing in TR55 is it's taking this rainfall depth and it's distributing it over a 24-hour period. And so our runoff hydrograph is based on that, based on the fact that the precipitation isn't all coming at once. So does everybody have a hydrograph so that we can go through the export procedure together? If you right-click on this window, maybe I better close that. You right-click on it, and what we're going to do is export/print. You know, this isn't like report-ready graphics. I mean, it's maybe good for visualizing the data, but it's not something you'd want to put into your dissertation. So if you want more control over what the axes look like and the color of of the trend lines and so on, you export the data. So we're going to do export print, and you can export this as an image file. These are just various image file formats, but really what we want to get at isn't an image, but it's the underlying data. So you select text/data, and then it can put it onto the clipboard so that then you could paste it into text editor, but I want to hang on to the file itself. So you browse to a location where it's going to save it, and it can do a .dat, which is just a text file, but to make it even more obvious for Microsoft Excel that this is just tabular text data, I'm going to have it the file extension .txt, and so crw runoff txt. And now when I click export, it's going to give us a bunch of options where we want it to be both of the hydrographs, not just one of them. So that's what this is. All data will be 2 of the hydrographs that we had on the screen there, now, along with the labels. And rather than being a list, we want it as a table. And now this first default option, I can't imagine why anyone would ever want this default option. What it will do is it'll have all of the data on a single row if you do subsets/points. But I think what we want is it to be in multiple rows in just a couple of columns, so that in one of the columns it's going to have time, and in another column it's going to have a runoff. So if you click to points/subsets and then export that, we can look and make sure if it just created that. Here it is, CRW runoff. If you double click, then it's just a text file, and those commas are delimiters, so that when you open the file in Excel, first of all, it's not going to see it when you browse to that location because it's not an Excel file right now. So if I go to the location of that, the WMS folder, it looks like there's nothing there to open. So you have to change it to either all files, or we know that it's a text file, so I'll change the file type to say text files, and then here's that CRW runoff text file. And it will give us an import dialog here, and it's a preview window based on the delimitations. And the default is that it's just delimiting based on where the tabs are, but we actually need it to delimit based on the commas as well. So if you turn that delimiter on, then now you can see with these guidelines that it's going to be in the right spot. So you can just click Finish at this point. And so this is the time in minutes, and then this is going to be the runoff in CFS. So we can create graphs with that at this point. So create a couple of hydrographs for both of those data sets. I almost said peak flow rate, which isn't right. This is flow rate over time. It's not just the peak flow rate. So it's a pretty big impact on having a curve number difference of 68 to 72. This illustrates that, I mean, essentially you're doubling your estimate of peak runoff just by a very modest increase in the curve number. And that gives you an idea of, you know, how little of a watershed needs to be urbanized for there to be a big effect on the runoff. You know, we've talked about, you know, when you disturb the land and start compacting the soil and increasing the impervious area, that a lot more of the runoff is going to make its way to the outlet and the water bodies that receive the runoff. And this illustrates the effect that just a small increase in the curve number can have. All right, well, for the watershed that you select for the homework, you're going to do the same things that we did in class today. Create a rational method version of the watershed, national stream flow statistics, and TR55. And ordinarily, I wouldn't mind if you picked a watershed anywhere in the world, except for the fact that the national stream flow statistics are only available within the United States. So, and of course, you're welcome to explore watersheds all over the place. And when we get into next week, when we're doing HEC 1, and maybe that's something that we'll take a look at, is maybe delineating some watersheds in the mountains of Europe, or maybe we'll go back over to the UAE where I know some of the watersheds there, or maybe even in China. Maybe we can delineate some watersheds and see if we get the elevation data we need. But that's it for tonight. Upload the new assignment by 4 p.m. next Wednesday, and I've got, I think, now 2 assignments in the queue for me to grade of yours. I'll get on those tomorrow morning, and if you have any questions as you're working on this next assignment, just let me know.